Before I explain almost all of the possible wave phenomena, I think you might have heard that there are different kinds of waves all around us, like sound waves that let us hear, light waves that let us see, water waves that ripple across a pond, and even invisible waves like radio waves, microwaves, and even X-rays. But what exactly is a wave? In simple words, a wave is just a disturbance through which energy travels from one place to another in a medium, like air or water, and sometimes even through empty space, like light from the sun reaching Earth. Also, just note one more thing which might come handy. The wavelength is simply the measured distance between one complete wave cycle, like going from the peak of one wave to the peak of the very next one. It essentially tells you how long a single wave is. Great. Now let's explore each of the phenomena one by one. Reflection. Reflection is what happens when a wave hits a surface and bounces back, just like a ball bouncing off a wall. You see it every day when you look into a mirror, when the light from your face hits the mirror and reflects back to your eyes, letting you see your own image. In this process, the light wave or light ray that comes in is called the incident wave or incident ray. The line drawn at a right angle to the surface is the normal, and the ray that bounces off is the reflected wave or reflected ray. The angle at which the light comes in is called the angle of incidence, and the one at which it goes out is the angle of reflection. And interestingly, both these angles are always equal. The same idea works for sound, too. When sound waves hit a large surface, like a wall or a mountain, they bounce back and create an echo. Refraction. Refraction happens when a wave changes its direction as it passes from one medium to another, like from air into water or glass. You can see this easily if you place a straw in a glass of water. The straw looks bent or broken at the surface. That's because light slows down when it enters water, making it bend slightly. The ray that falls on the surface is called the incident ray. The one that bends inside the new medium is the refracted ray. And the line drawn at a right angle to the surface is the normal. The amount by which light bends depends on the angle of incidence and the refractive index of the medium, and this relationship is described by Snell's law. Diffraction. Diffraction is the spreading or bending of waves when they pass through a narrow opening or move around an obstacle. You can see it in this animation. As soon as blue light passes through this slit of 0.1 millimeter diameter hole, it diffracts and forms concentric rings. If we change the diameter of the hole, or if we change the color of the light, then the pattern of the rings also changes. The extent of diffraction depends on the wavelength of the wave and the size of the opening. We see the effect clearly only when light passes through tiny slits, like on the edges of a CD that shows colorful patterns. Interference. Interference happens when two or more waves meet and combine with each other. Depending on how their crests and troughs align, basically how their peaks align, they can either strengthen each other or cancel out. When the waves add up and produce a larger effect, it's called constructive interference, and when they oppose each other and reduce the effect, it's called destructive interference. The rule behind this is the principle of superposition, which says that the total effect at any point is just the sum of all the waves meeting there. One of the most famous demonstrations of interference is Young's double-slit experiment, where light passing through two narrow slits forms a pattern of bright and dark bands on a screen, which is clear proof that light behaves like a wave. Polarization. Normally, light waves from the sun or a torch, being an electromagnetic wave, vibrate in all directions perpendicular to their path, making them unpolarized. This means if light is traveling forward, the vibrations happen side to side, up and down, and everything in between, like a rope being shaken. But when light passes through certain materials, like a Polaroid filter, or reflects off shiny surfaces like water or glass, its vibrations get restricted to just one plane, and this is called polarized light. You can actually see this effect with polarized sunglasses. They block certain directions of light and reduce glare, making the view clearer and more comfortable for your eyes. The concept of polarization proves that light waves are transverse, which means they vibrate sideways rather than back and forth. Total internal reflection. Total internal reflection is a special behavior of waves that occurs when it tries to move from a denser medium to a rarer medium, like from water to air or from glass to air. Normally, when light crosses from one material to another, part of it bends or refracts, and part of it reflects. But if the light hits the boundary at a large enough angle, called the critical angle, then something interesting happens. Instead of passing through, all of it bounces back inside the denser medium. This complete reflection is known as total internal reflection. You can see it when you look up from underwater and notice a mirror-like surface above, or in the sparkle of a diamond, which traps and reflects light within. This is also the principle behind optical fibers, the tiny glass threads that carry data as light signals in modern communication. Dispersion. Dispersion is the phenomenon where white light splits into its different colors when it passes through a transparent material like a glass prism. This happens because light is made up of many colors like these, and each of these colors bends by a slightly different amount when refracted. The refractive index of the material is not the same for all colors. Violet light bends the most, while red bends the least. This separation of colors forms a beautiful spectrum, which you can see in a rainbow, which is nature's perfect example of dispersion. Scattering. Scattering happens when light or any wave strikes tiny particles in its path and gets redirected in different directions. It's the reason why the sky looks blue and sunsets appear reddish. When sunlight enters the atmosphere, it meets countless air molecules and dust particles. The shorter wavelengths of light, like blue and violet, get scattered much more than the longer wavelengths, such as red and yellow. Our eyes are more sensitive to blue, so the sky appears blue during the day. At sunset, sunlight has to pass through a thicker layer of air, so most of the blue light gets scattered away, and the remaining light reaching us are mostly reds and oranges. Absorption. Absorption happens when a wave, instead of bouncing off or passing through a material, gets its energy taken up by that material. You can feel this easily on a hot day. For example, a black shirt absorbs much more sunlight and feels hotter, while a white shirt reflects most of it and stays cooler. Different substances absorb different wavelengths of light, and that's why objects have colors. They absorb some colors and reflect others. In sound, soft materials like curtains or foam absorb sound waves and reduce echoes in a room. Rarefaction and compression. Unlike light, which is a transverse wave and vibrates sideways, sound travels through air by pushing and pulling the air particles back and forth along the same direction as the wave moves. When the particles are squeezed together, forming a region of high pressure, it's called a compression. When they are spread apart, forming a region of low pressure, it's called a rarefaction. Diffusion. Diffusion of light happens when light hits a rough or uneven surface and scatters in many directions instead of bouncing back neatly. That's why you can see everything around you, even when the light source, like a bulb or the sun, isn't directly in your line of sight, as light spreads out and fills the space. A polished mirror gives a clear reflection because its surface is smooth, but a wall or paper has tiny irregularities that scatter the light in all directions, creating what we call diffused reflection. Attenuation. Attenuation means the gradual loss of a wave's strength as it travels through a medium. You might have noticed how sound becomes fainter as you move farther from its source. That's because of attenuation of waves. Resonance. Imagine a spring mass system having a spring constant as K equals 200 newtons per meter and mass as 2 kilograms. Its natural angular frequency, omega, will be square root of K over m, or 10, and thus its natural frequency will be 10 over 2 pi, or 1.59 hertz. Now, when we apply an external periodic force, that is, when we keep pushing or pulling the mass back and forth with some driving frequency like this, the system starts to perform forced oscillations. If the frequency of this external force is far from the natural frequency, either smaller or bigger, doesn't matter. The oscillations remain small. But as the driving frequency gets closer to the natural frequency, the system begins to respond more strongly, and the amplitude of oscillation increases rapidly. This special condition, where the frequency of the applied force matches the system's natural frequency and the amplitude becomes maximum, is known as resonance. At resonance, energy is transferred most efficiently from the external force to the system, causing large vibrations, just like pushing a swing exactly in sync with its motion makes it go higher and higher. Even bridges and buildings can experience resonance during strong winds or earthquakes if the shaking matches their natural frequency. Standing waves or stationary waves. Standing waves, also called stationary waves, form when two identical waves move in opposite directions and overlap. Like when a wave on a string reflects back from a fixed end and meets the next incoming wave. Instead of traveling forward, the wave seems to stand still, creating fixed points that never move, which are called nodes, and points that vibrate with maximum energy, like these ones, are called antinodes. You can actually see this if you pluck a guitar string. The wave doesn't travel across the string. It forms a steady vibration pattern between the ends. Doppler effect. The Doppler effect is what you hear when an ambulance or train passes by. The sound seems high-pitched as it comes toward you and lower-pitched as it moves away. This happens because the sound waves get squeezed, which means it has shorter wavelength, or higher frequency, when the source or the object making sound moves closer, and stretched or longer wavelength or lower frequency when it moves away. The same effect happens with light waves, too. Astronomers use it to tell whether distant stars or galaxies are moving toward or away from Earth. A red shift in such observations means they're moving away, as light waves stretch and have a longer wavelength, and a blue shift means they're coming closer, as light waves compress, meaning a shorter wavelength. Finally, we have beats. Beats occur when two sound waves of slightly different frequencies meet and interfere with each other. Instead of producing a steady sound, they create a rhythmic rise and fall in loudness. The rate at which you hear these pulses depends on the difference between the two frequencies. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member. So good!